This session is going to combine support vector machines, which is a new algorithm which we'll be looking at, with how you tune machine learning algorithms to optimize them even further than ideas that we've previously discussed. And we'll have a notebook demonstrating the two after these slides. So firstly, we will look at support vector machines and why they're different from what we've previously looked at, i.e. random forest, decision trees, naive Bayes, and so on. And then looked at how we can tune our models. So not just support vector machines, how we can tune all of our models using the internal parameters. So just slideshow this. Okay, so support vector machines, they're classifiers that try to solve a geometric optimization problem. And what you'll see that some of the ideas behind SVMs are very similar to how we solved regression problems. And what we're interested in is we have data with multiple classes, so it's a classification problem, and we're trying to split the feature space using hyperplanes. So in linear regression, we were interested in fitting lines through our data. With support vector machines, we're interested in fitting lines that split our data. If we have an example like this, we have people that have anxiety and those that have depression, and this isn't in a world with easy classification because some people will have both. So yeah, this is just a binary classification. And then given certain prescriptions of medication that they've had over their life, can we predict if they have anxiety or depression? So for anyone that is a clinician and is looking at this data thinking this looks weird, don't worry, it's just a toy example that I made up. So there's no bearing in the real world, it's just for demonstration purposes. And so yeah, we can take this data and we might notice that maybe people who largely have more Lexapro prescriptions than any of the others, they tend to have anxiety, and maybe people who have depression. One thing which is useful, so as we've gone through the week, we're trying to introduce the ideas of how you engineer your data to make it easy for classification. A lot of the work is done up front, engineering your data before you even get to do classification. So you can take a data transformation here because we can have a lot of outliers, perhaps, if you're plotting maybe Lexapro against Xanax, purely because we're using raw numbers. So this would indicate that they've been given Lexapro 55 times throughout their life compared to Zoloft. And what might be easy is to normalize this data by saying what percentage of prescriptions have been taken up by Lexapro against Zoloft and Xanax and so on. So this is quite a common technique, especially in neural networks. You'll find that all of your input data usually has to be scaled in this way between values between 0 and 1. So this is a pretty common thing to do in feature engineering. With that out of the way, let's plot them. So there's a handy function in R called pairs, where you can, again, because everything's vectorized in R, it can take all columns and it'll just plot them all against each other. So you can see what we have. If we were to take Lexapro versus Zoloft, we can see that clearly you can define some hyperplane or line that can split this data, but maybe not so much in Weyl-Buterin, because these 3 points, they are problematic. You can't draw a line to separate these. And in the worst case, we have Zoloft versus Weyl-Buterin. So clearly you can't draw a line to separate those classes. We'll take Weyl-Buterin versus Lexapro. This is the easy case. So let's see how SVM can solve the easy case first. And again, the ideas are very similar to linear regression. We're going to start off with a line or a hyperplane, and clearly this line splits the data perfectly. And we can measure this in certain ways. So we can take our line and take equidistant margins to the data point either side of the line. So this is one point and this is another point. These margins, they are of equal length on either side of the line. And we can take multiple lines and do this actually. And what we can do between these two lines is say, well, the margins for the red line, they are larger than that of the blue line. So we could probably conclude that the line which gives you the largest space between our two classes is the better line, i.e. in this case, the red line. You know, they separate the data with the most margin, or the most space, if you like. These two vectors, which we expanded our margins out to, well, these are called the support vectors. This is where support vector machines get their name from. You start off with lines, and you want to find the optimum line where you're taking the distance from the line to the support vectors. And the aim is to find the hyperplane that splits the data with the maximum margin W. And the length or width of W comprises of geometrically equidistant margins either side of the hyperplane to the support vectors. The support vectors are the closest points to a given hyperplane and are denoted with the coordinates xy, so which is an xy space, i.e. a vector. So this is where support vector machines comes from. And hyperplanes, and usually they're just chosen at random, and you try to find the best one. And this is what we'll try and go through in this case. So just to, you know, we always need to be thinking about training and testing in this case. If we look at our training data here, and we look at these two lines, we might conclude that this red line is the best one. But obviously, when we have test data brought in, so this is a data point here, and we want to classify it, we have another one here. So those are fine, and you keep adding test points, but it may well be that our test data doesn't behave exactly how our training data spells out the problem for us. So during training, we're going to find an optimum hyperplane, and depending on our training data, how it's plotted, it will give us a different hyperplane. And we're going to use the optimum hyperplane with unseen test samples and see how they correspond. Do they fall the right side of the hyperplane to classify them accurately? And we just saw how error could be introduced potentially, because we're adding new test sets, and they might not necessarily obey the same correlation as the training data, although they should approximately do that. You know, just to envision an entirely new test set. So we train our data like this. We found that this was the best hyperplane, so we keep it there, hold it in place, and then here comes our test data. And we can see just this point down the bottom here, this is where we get some error. So clearly, again, training and testing, just to demonstrate in SVM, is just as important as in any other algorithm. And, you know, this is easy, right? Okay, so although we got this wrong, there will be some error in the training and test data. I think what you can all agree on is that this particular scenario where you've trained on this data, which in training you can get a perfect classifier, and in the test data you might introduce a very small amount of error. I think what you can agree is that this is a very easy problem to solve, and we often call these linearly separable or a hard margin problem. So you can expect to find a perfect classifier in some cases. Like in logistic regression, we saw that you can have nice data, but then we looked at real world data where there's some overlap there. So clearly not everything in the world is a linearly separable problem. That being said then, so let's look at what a non-linearly separable problem might look like. And I think we're going to look at Wellbutrin versus Xanax here. So we see we have this a bit problematic, these three data points here, and here they are. So let's see how we can try and find an optimal line here. The first thing to say, let's try this hyperplane. We can see immediately there's some error, because the red is falling, data point here is falling on the wrong side of the line. Similarly, we have another line here, and what we're saying is anything past this line, the green line on the left-hand side, should be classed as red, but we have these two data points here, which are classed as blue, which are actually blue in the ground truth. And you know, you can draw any type of line through here. It doesn't matter what you do. You will never, even in training, find a perfect classifier. And so what we can do, instead of using a hard margin, we can use a soft margin where we allow some form of error either side of the margin. And purely we're doing this, one, because we know data isn't so kind to us, but also we're going to look at how overfitting can come into play as well. So, this is a typical thing in SVM. They overfit. They're really good at finding the optimal margin, even sometimes a perfect margin to training data, because they're just solving a very simple geometric problem. They find the line. However, when you put new test data over the top, you tend to see quite a significant drop in accuracy on the test data. And usually this is because you've encountered something called overfitting. You've relied too much on the training data, and therefore you don't generalize the test data as much. So what SVMs can do, they can use a soft margin. So during training, using a soft margin where we allow some acceptable amount of error, we can try and reduce that problem of overfitting. So, we could have a margin which allows, 2 misclassifications, 3 misclassifications, and what you want to experiment with is how much error you include and how that increases the accuracy in your test data, or rather reduces the difference between the training accuracy and the test accuracy. And you'll see that that's actually something that you need to look at in neural networks, or it pops out quite frequently in neural networks, how the loss function that you have. So you have high accuracy in the training set, but low accuracy in the test set, means you're overfitting, you need it to converge. So this C parameter in SVM allows us to do this. Basically, the C parameter, or sometimes called a cost parameter, allows us to define how much error we deem acceptable during training. So let's look at this overfitting issue. So we've got our training data. We have a line with very thin margins. We're not allowing much room for error in our margins here. And what we could do, we see that data points don't tend to correspond well using test data. And what we might decide to do instead is that we can use a wider margin. So this is basically increasing the value of C, allows some form of error in C. And, we do this not because it makes our training accuracy better. Remember, training accuracy isn't really that important to us. It's the test accuracy. So we do this to help generalize and reduce our error in the training set, i.e. we reduce overfitting. Okay, so a completely inseparable problem. This is where SVM gets very interesting. We could have an example like this, and you would never be able to draw one line, straight line, that would split the data perfectly. Because if you drew it here, obviously, we're misclassifying this red space. Similarly, if you draw it here, it's misclassifying these red data points. So how does SVM get around this? And there's a really cool thing that SVM use called a kernel trick. And we're going to transform our original data. And actually, we're going to transform it by embedding an additional dimension in our data. So at the moment, we have X and Y. We're going to drag our data in certain directions along a new dimension called Z, i.e., into or out of the page, however you want to think about it. So let's consider the quadratic transformation, which works well for that particular graph I just showed you. So we're going to embed a third dimension Z, which is equal to X squared. Why this works well in this particular case, our quadratic function, the further you move away from 0 in either direction, the response will be to increase the value either side. So that means if we take our data, which originally looked like this, we're going to bring these red points closer to us out of the page, and the blue points will sit at the bottom. So there'll be a valley that we're looking top down on, and we're bringing these red points closer to us while we keep the majority of the blue points where they are. And it looks a bit like this. So we've embedded our third dimension in. And now what you can see, there's a big gulf in between the red and the blue data points. So you can just easily plot a line in between those two classes. And just to show you how this works, once you've done this transformation, you can just use a simple linear regression or simple linearly separable SVM problem to solve this. So here we are. This gray hypersurface is not a hyperplane anymore, it's a hypersurface, clearly intersects the 2 points perfectly. So we just, in a way, manipulate our data in the first place using a kernel trick to result in a far easier problem. And I know what you're thinking. This now looks like we've cheated. And what we're not going to do is leave the data as it is and say, okay, we've manipulated our data until we can get to a point where we've tortured it so much that we can now separate it properly. We need to bring this data back to the dimensions that it originally came from. And so there is a way of doing this, which I will demonstrate now. Actually, I think it's this one, isn't it? Yes. So we've got our quadratic function we've plotted to fit our data, which is this bluey red curve, and intersecting it is the hypersurface that SVM has found. So this is how we're going to bring back this quadratically transformed data back to our original 2D data set. So if we look, what we're going to do, we're going to bring down the view and go underneath this hypersurface. So you can see where it intersects, somewhere at the bottom of this valley. You can see this gray rectangle in the middle. And as we start to bring it down, we're going to look from the bottom up, so it's back in 2D. Okay, so here we are. So you can see, looking top down from this boundary, anything that is within the blue boundary here gets classified as a blue data point. Anything in the gray boundary, and I tried to add a bit of transparency, but I can't seem to get it working. Anything that's fallen within the gray boundary, this is classified as a red point. So what we did is we intersected our kernel function with the hypersurface, which was easily plotted with our newly transformed data. And where they intersect, you can return the original 2D dimensions like we've done here. So, don't think that we're just going to leave the data with all the transformations in place. We definitely relate it back to our original boundary space. So kernel tricks, which is a really cool thing about SVM, they transform non-linearly separable data so that they can be linearly separable. SVMs will simply apply the same optimization methods as before. And remember, because we're now adding an extra dimension, it's not just a hyperplane anymore, it's a hypersurface. And actually, just like in multiple linear or multiple logistic regression, most of these problems, you'll never plot in a hyperplane because we always usually have more than one feature. So we're interested in plotting the best hypersurfaces in these cases. There are different kernel functions as well. So that was an example of a polynomial kernel function, just z equals x squared. They can get really obtuse, like z equals x squared plus y cubed plus z, whatever. They can get really, really more convoluted, and it's the job of SVM to try out different kernels as it does that. So that is optimizing first the kernel function, and then things like C as well, the cost parameter. Just to show you another example. So this is a Gaussian kernel function. Again, this is like contour plots where you look at mountains, if you're going mountaineering or so on. These blue dots, what we want to do is represent these as higher data points. So we're going to use a Gaussian or a normal distribution where the closer you get to the center, the more we're going to bring these blue data points out towards us from the page, as you can see here. So, there's easily a line you can draw between those. And the way you visualize this is a nice video I found. So if we've got our blue data points in the middle and our red on the outside, we use our Gaussian kernel to transform our data. So the blue points, they kind of sit at the bottom of this 3D valley. We use SVM to get a linear hypersurface. And now we're going to overlay that ring where the kernel intersects the hypersurface back onto our original data. And then if you go and we take a bird's eye view of that, we can see that, clearly we've got not just a straight line, straight boundary as in the quadratic kernel that I showed you before. We've got, a circle. So these boundaries that SVM find, they don't need to be straight lines. Using the kernel trick, when you bring the boundaries back onto the original data set, they can be all sorts of funny shapes. You can have things like this. This is a sigmoid kernel. So you can see you kind of get this S shape. Or you can have really obscure ones. There's a radial basis kernel, and you can find SVM solving these really strange problems. So SVMs, they can produce really weird and wacky boundaries. So that's enough of that. So just in summary, before we look at hyperparameter tuning, which we'll use SVM as an example, support vector machines, they are a coordinate space classifier. Their main aim is to split the data using mathematical concepts or equations, things like polynomial kernels and so on. SVMs find the best hyperplane by using optimization techniques, hard, soft margin, and so on. And they use the training testing methods just as we described previously. The cool thing, remember, about SVMs is the kernel trick, and it transforms our data into a higher dimension so we can then make the classification problem easier, and then overlays the classification boundary back on our original data. There's a few interesting strengths and weaknesses about SVM. As you can imagine, because it's just optimizing based on coordinates, it can work really well on small data sets. If you have small data sets, SVM might be a good bet. Be aware, though, on the flip side of that, it can be susceptible to overfitting, just because it finds it easy to find a boundary on your training set. It might underestimate the test data. It can solve nonlinear problems, which is good. We showed the kernel trick. It doesn't just have boundaries with straight lines. It's got all sorts of curvy lines. It can be computationally expensive, though. So think of all the things it's going through. It's got to go through different types of kernels. It's got to measure lots of distances away from each other. It's got to do data transformations and then overlay them back on. So it can get, it can run quite slow sometimes. To understand SVM, I think a strength of it is that it's just using simple mathematical techniques. So like if you can get your head around residuals and calculating R squared and SS fit in linear regression, you'll have no difficulty at all understanding why SVM finds boundaries. However, these two are linked. So no interpretability in the real world. It's not no interpretability. It's got less interpretability of models that output probabilities. So remember, naive Bayes, logistic regression, decision trees, random forests, they all have class probabilities associated with them. So not only do you get classified as 0 or 1, what's the probability of that? Well, in SVM, there's nothing really like that because it's just measuring distances. If you have a data point, you can't really say, well, the probability is this. All you can say is that the distance of you from some obscure hypersurface is this. And so the interpretability does lack a bit using SVM. Yes, so and this point here does not rely on trends in data as a strength. I think what I'm trying to say here is that you don't need lots of big data sets to pull the trends out. It's just measuring distances between points like in linear regression. So yeah, I think that's a strength as well. Again, that just says you can use me on smaller data sets. Okay. So we're going to talk about something really important that you should always do in machine learning, and that is something called hyperparameter optimization, look at different sampling methods, and finally, receiver operating characteristic analysis, or ROC analysis. And This works on any machine learning algorithm, or most machine learning algorithms at least. We'll use SVM as an example. And just remember, we had this thing called the cost parameter to specify how much of tolerance of error you have during training. Well, what you would like to be able to do is try different values of C and then look at the resulting test accuracy. And you can clearly see that one particular value of C will have the highest corresponding test accuracy. So we're trying to tune these parameters or hyperparameters like C to achieve the best possible accuracy. Let's start off with hyperparameter tuning. In decision trees, we had tree length. Random forest, we had the number of trees. And remember, the default random forest package had a really nice visualization. It plotted the error as you add more trees. And there was also something called mtry in random forest. So, you know, when you split the nodes, you don't consider all features in each node. You just select random number of features and you optimize on those. SVM, there's the C parameter, or the cost parameter, and as well as kernel type. And what we'd like to do is just mess about with the values across these parameters and see which gives us the best test accuracy. That's the basic idea of hyperparameter tuning. And really, this is no different from the way M and C are optimized in linear and logistic regression. You know, they've got those built in, but what we need to do here is we need to try different values ourselves, build them in. And there's a nice package in R, which I'll show you to help us automate this. Okay, yeah, so any machine learning technique, they will often have parameters that you can change to do hyperparameter tuning. Okay, so optimization using hyperparameter tuning, let's have a look. So the aim is to find the right value for the parameters that give the optimum accuracy, sensitivity, or specificity. So far, we've only been looking at accuracy. When we look at ROC analysis, we'll introduce these concepts of sensitivity and specificity. But the point is, we use hyperparameter tuning to find, you know, the optimum value of these. And you can think of it like this. There'll be some point along this curve. This is called something called cost curve or loss or error curve. There'll be some point along this curve which has the lowest error, okay, which is down the bottom of this valley here. And you can think of nudging your value parameter and seeing what the resulting error is. And what you would like to be able to do is to get it to come all the way down until you've got the minimum error. Now, you don't know what this curve looks like in the first place. If you did, you would know easily how to get to the least amount of error. So this doesn't exist. We're in the dark and we need to nudge these values about and just look at the corresponding test data. Now, things can get difficult because you might think, if I'm using certain values of C, I decrease C and or increase C and finally, I get to the bottom of this valley. I think, oh, I'll keep decreasing it even further to see if I can go further. And you notice that the error starts to increase again. And that's because in some points you have the cost curve might look something like this, where you have local and global minima. So you want to get to the global minima in this case. Let's have a look at a few. Well, we'll look at brute force mainly. Marcos is going to cover gradient descent in neural networks. So let's look at brute force. We just nudge a parameter until accuracy improves or stops improving, or so on. You find this valley. So you can nudge the C parameter in this way. I think what you'd have to consider, though, is that you'd have to try both directions. Which range do you use? How much do we increase or iterate by each time? Again, this local minima problem, brute force tends to get foiled by this issue, and it's slow because we have to try nudge it a small amount at a time. I won't say much about gradient descent. It just allows us to assess if the direction we're traveling in is increasing accuracy more or less than if we nudge the parameter a smaller or greater amount. So if we have a cost curve here, we can take the tangent between two data points and clearly see that the error decreased a lot more. The slope of this line is far greater than that if we took these two data points. I'll let Marcos go through this with you when he goes through neural networks. Basically what you do, so if we have a C parameter, actually there's more parameters you can optimize in certain types of SVM. You can have a grid of parameters. So often hyperparameter tuning is sometimes called grid search. And we're putting in various different values of C against various different values of gamma. And there'll be a point where you minimize the error, which you could choose any of these combinations here, any of these 6 combinations. So yeah, think of parameter tuning as mapping out your different values of your hyperparameter across a grid. Obviously, if you have 3 hyperparameters you tune, you'll have a hypercube, if you like. So when you do this, though, because you're trying out all these different variables, every square in this grid search, you are running SVM, which means in this case, it's 7 times 8 or 56 times. So what you'll find is when you're doing hyperparameter tuning, this is where it takes a long time to train your models and get the best accuracy, is because you're doing hyperparameter tuning. You're running the machine learning algorithm loads of times. And again, just taking different data samples, so we're leading into different sampling techniques now. Depending on how you subsample your data, remember we took random samples of data to be in the training set and random samples to be in the test set. Well, if you repeated that process multiple times, on the whole, you might find that grid search you find similar values for your hyperparameters. So most of these are the same. But you might get the odd random sample, which throws up a completely different story. So, what we would like to do is to stabilize this hyperparameter tuning process by using multiple different types or multiple different samples of our training data. And this brings us into sampling methods. There's a really common method which goes beyond the simple train and test. And this is called K crossfold validation. So when people do hyperparameter tuning, they're usually combining this with this method called K crossfold validation. It's really simple. In the case of K equals 3, we just repeat our train test method 3 times. So it means we'll end up with 3 randomly chosen training sets and their corresponding test sets. And yeah, I said we do this because it will end up presenting training sets. One training set on its own might not accurately present the data in a generalized way, because we might take another random sample and suddenly the picture looks a lot different. When we're trying to tune our data, we might end up with this scenario. So what we're trying to do is average the thing, but even back in school, if you wanted to get a stable result, you take an average of multiple experiments, and this is what we're doing. This is what K crossfold validation is about. I will say you should, even though we are producing within the K crossfold validation procedure, we are producing our test sets in there. Again, when you report accuracy, you should always report on an additional test set, always. So let's consider some of the nuances about K crossfold validation. If we're training K models, you should be aware that they don't share any knowledge with each other. So if K equals 3, when you take your first training set and then you use the internal test set to assess the accuracy, when you come round to K equals 2, none of the knowledge you've gained from K equals 1 gets shared with K equals 2. So all of the folds, they're kept separate from each other. So that's the first consideration. So what that will mean, though, is one particular data point may get used in a training set in 2 different training sets, and it may get used in 2 different test sets. So it means that you have to consider that you're getting multiple decisions on the same data point. So how do we resolve this? So like in random forest, we can take a majority vote. Think of the worst case scenario here. You have 2 K equals 2, and one says the class is this, another says the class is that. Okay, what do? You have to just say, well, it's 50-50, which isn't good enough. However, you know that there's going to be an associated probability with those. So what you tend to do is average the class probability. Okay, yeah, so we can take the average class probability. So, random forest kind of has almost a version of K, it should say almost K crossfold validation built in, in the sense that it does randomly bag data to send down a different tree. However, what we're saying in K crossfold validation here, the traditional K crossfold validation, is that through each fold, it uses the same model to go through, whereas clearly in random forest, each tree is different from each other. So this is kind of like K crossfold. It's not exactly the same. It's different. So it's often referred to as bagging in random forest. Second consideration. So this is actually a good thing that multiple data points get used in multiple different test sets, because then we can get an average, and this is what we like. It makes things more stable. There's a way you can actually, K, as you increase K, the more likely it is that every single data point will get used in multiple test sets. Okay. You can also enforce this. This is a special type of K crossfold validation where you take all the training points, training data, apart from one point. You train on 99.999% of the data and you test on just the remaining data point, and you just keep doing this until you've gone through all the data points. So that's an extreme way of doing it. If we have 1,000 data points, we would have 1,000 folds in this case. So it's a good thing that we have multiple data points going down different folds. Third consideration, this is what K crossfold validation is for. Really, is hyperparameter tuning, and this is only ever done in the training set. The crossfold validation takes place in training. Okay. And hyperparameter tuning is combined with crossfold validation to stabilize, not only optimize, but get a stable estimation of what the hyperparameter value should be. That's a really good point about crossfold validation. We're using it to get our most optimum and stable hyperparameters. And any tuning of any machine learning algorithm you do is always done in this crossfold validation stage, or even in a training stage. Just think of it as a training stage. So whenever you tune something, you always do it with the training data. So if you were to run SVM 56 times using grid search, because you had 2 hyperparameters to tune, if you were doing this with K equals 3, you'd have to run SVM 168 times. So a lot of people find that I'm going to introduce the Carrot package, which automates this for us. And the common complaint I get every year is, why is it so slow? I'm not using this package ever again. And the reason is because it's going through so many times. Yeah, so imagine doing this with the leave one out method. You'd be running it loads of times. And the fourth consideration is that we'll have multiple separate models. So, you'll have a training and test set for K equals 1, you'll have a training test set for K equals 2. And the idea is, we're talking about stability here. When you take the average of your results, you would hope that a stable model would mean that regardless of which fold you look in, the accuracy and the hyperparameters converge to the same values. If you have accuracy, which is vastly different across the different folds, then your model isn't stable. Maybe not the model, but your data doesn't allow your model to become stable enough. But by looking at these, this is useful because we have a range of accuracies and we can just report exactly how stable our model is. Just remember, crossfold validation is done in training. We always report our final results on a test set. So simple rule: tuning is done with training data, and crossfold validation is part of the training process. Final accuracy, sensitivity, specificity, whatever it is always reported on the independent test set. Yes, so it allows us to see how stable our model is. Okay, now ROC analysis. Again, this is another staple of machine learning. You should always do it. So let's have a look. So we're talking about the receiver operating characteristic, or ROC. And we're going to expand upon metrics of accuracy by including sensitivity and specificity. Sensitivity is a way of saying how accurate does it predict the positive class accuracy is an overall measure. Sensitivity is how accurate you can predict the positive class. Specificity is how accurately you can predict the negative class. So we'll look into these in a little bit. The point is that when you were computing your confusion matrices before, you're usually doing so where you say, based on my class probabilities, say it belongs to a given class. If the class probability is above 0.5, or I've seen in some cases the default confusion matrix can arise where you're optimizing on accuracy and not necessarily sensitivity or specificity. And you might not want to accept these thresholds. You might want to play about with these thresholds a bit. You could choose 0.5 as your threshold, or you could choose 0.75, depending on the kind of problem that you have. Let's try and visualize this and think about this. So if we have a classifier that has an overall accuracy of 84%, a classifying between COVID-19 and non-COVID-19 samples from a test, what we would really be interested in, because it's a spread of a deadly virus, we would actually want to pick up every single person that does have COVID-19, even if this means that we falsely label too many people as having COVID when they don't. So if you were optimizing accuracy, you wouldn't necessarily be interested in maximizing the number of people you pick up that have COVID. But if you're maximizing sensitivity, you are definitely interested in picking up as many of the positive case as possible, even if it means overestimating COVID-19 in the population. Okay, so if we just remember that each data point will be given its own class probability. So we've taken a training set, and here is the result in a test set. And Roc Analysis, the first thing you do in Roc Analysis is these probabilities you see now, these are on the test set doing crossfold validation. So this is still in training at this point. However, you remember when you report accuracy on the test set, you would also get something similar. But just pretend now that we are doing our crossfold validation. We've looked inside one of the folds, we've trained it, and on the test set, this is our predicted class probabilities. Okay, so we have our COVID-19 in the red and our non-COVID in the blue. And accuracy, or if you specify, generally a point 0.5, you're setting your threshold here. So anything to the left of this threshold is classed as COVID-19 in your predictor, in your classifier. Anything to the right is classed as COVID-19. So here, this section, just this red section, clear red section, are our true positives, because we've said that they're predicted as having COVID-19, and they actually do. We have our true negatives, which is the opposite to that. This region here contains false positives and false negatives, because on the left-hand side of this threshold, we have people which are classified as not having COVID, but clearly these people do have COVID. And then obviously we get the opposite to that, people which don't have COVID, but they are getting classified as having COVID. And the equations for sensitivity and specificity are like this. Sensitivity is the true positives over the true positives plus false negatives. Specificity is true negatives over true negatives plus false positives. And actually, accuracy is the average of sensitivity and specificity. So what we could do is actually set, if we really wanted to pick up all the COVID-19 cases to prevent the spread, we could set our threshold here instead. So instead of being 0.5 or a threshold which maximizes accuracy, we could set a threshold which maximizes sensitivity. So if you see here, anything onto the right of this threshold is classified as COVID-19, which is the entire distribution of people which actually have COVID-19. So this means that all of this red curve are true positives. So, but we do still have some false positives, because this blue curve gets classified, anything to the right of this blue curve threshold is classified as having COVID, and they don't. So we have a larger amount of false positives than before. However, we have no false negatives, which is okay, because it might be more important to us to reduce the false negatives and accept a higher number of false positives, which is fine. Okay, so if you see them side by side, we have no false negatives on the right, but we have more false positives. So it just depends on your situation. In this case, you want to pick up more COVID. If it costs a lot of money to take a case forward once you've identified them as having COVID, I don't know, maybe just an efficiency savings, and you might want to maximize specificity instead. There you go. At least you have the flexibility. And again, you do this during crossfold validation during the training process. Now, you know, this does sound like parameter tuning, and I would argue it is. It's just another parameter. So think of it like hyperparameter tuning, just in the case of, you know, the final probability threshold. So, you know, we can bias our classifier to favor specificity or sensitivity. There's a trade-off. It would be good to visualize the exact amount of trade-off easily. We could nudge these values and see what the corresponding sensitivity or specificity is like. But the ROC analysis allows you to visualize all thresholds in one go. So this is a Roc curve, and this blue curve here is our result. So this is made of a number of points. We're nudging the probability threshold as we build this curve. Okay, so these are all just loads of little data points put together. And what we're saying is that at this data point here, whatever the threshold was, our sensitivity is 80%. However, we have a false positive rate corresponding to about 15%. Okay, so true positive rate is sensitivity. False positive rate is 1 minus specificity. This yellow line is the line of chance. So no matter where you are across this line, whatever point you are across this line, it's just like flipping a coin. The true positive rate equals the false positive rate. This is the worst place to be in. This is a classifier which just cannot decide. Okay, and so if that's random chance, if we draw a line in the opposite direction, usually what you find, this point here where they intersect, this maximizes accuracy. It doesn't maximize sensitivity or specificity. But as we just said, we can choose, and by the way, this is usually where your confusion matrix, default confusion matrix comes from, this point here. But we can choose a point up here instead. So we're maximizing sensitivity. So instead of having 0.85% sensitivity, we can have 0.95% sensitivity, but we must accept then that we have increased our false positive rate. We have this AUC as well, area under the curve. So this represents the total amount of accurate measurements you can, predictions you can make across all thresholds. So a lot of people use AUC instead of accuracy. It just says, given my data, this says more about the data that you have than anything. Given the data I've put into my model, the absolute best I can get across any threshold at all when I combine them is this much. So that's AUC, and it's important as well. It's a nice interactive demo of this you can look at. And again, just to say that the aim of the game then is to push this curve into the top left. So this data point here, where we've chosen just one threshold, this is a perfect classifier. So the top left is where the perfect classifiers are. Yeah, so we want to move this curve, budge it up to the top left, as you see here. And there's a few things you might encounter when you're plotting Roc curves. I've seen this quite a lot of times. This basically means you've put your labels in the wrong way around. So you know you've got your labels like diabetes, yes or no. You've put in your predicted class probabilities, and somehow the labels you've got them the wrong way around. So instead of coming up into the top left, it goes into the bottom right. It does still mean, though, that this is a good classifier, even if you've got your labels incorrect. You don't want to be in the middle. That's the main thing. But obviously, Roc curves are always presented as being in the top left. Okay. And then another one you might get, this crops up a lot, is where you have like a sort of an elbow, so two straight lines. This means that you have put in your class, you've put in your ground truth labels, which is 0 or 1, and you've plotted that against the predicted class labels, where really you should be plotting against the predicted probability to get a nice smooth curve. So if you see like a, like an elbow in your Roc curve, you've not used the class probabilities. So, just two common things you might come across. So in summary, there is much more functionality beyond the default parameters of an algorithm. We can tune hyperparameters. And again, always done in training, always done in training. By the way, just before I go on, even though we get the best threshold for a Roc curve during training, again, just like accuracy, you should always run a Roc curve then on the test sample just to report the sensitivity and specificity range on the test set. So you do Roc analysis in the training stage just to get the best threshold, and then you also present it as you would with accuracy on the final test set. So we can use hyperparameter tuning. We can use resampling methods like Crossfold to get our best estimate of our hyperparameters. And we can also bias our results using ROC analysis. So we're going to basically look at the Caret package in R, which is a really famous package in R. It's an all-purpose machine learning package. There's even a Python implementation of this. And yeah, we will use this in our notebook session to see how we can do all of the things we've just talked about in an automated fashion. Okay, so let's take a look at the support vector machines notebook, where we look at hyperparameter tuning and Roc analysis. And a lot of this notebook revolves around the Caret package to help automate hyperparameter tuning. But we'll also look at the Yardstick package, which helps us do ROC analysis. And there are actually quite a lot of different libraries that help you do ROC analysis. You have the RocR, PRoc, and so on. So I'm just going to use Yardstick. It's part of the library, the Tidyverse package. So let's just have a look. We're going to use the Humvar dataset just for this notebook because it's a nice, easy dataset to demonstrate on. Just going to very quickly take a random sample of training data, and again, another random sample for our test data. Technically, you should do this in a way where you ensure that there isn't, that there's no way one of the test samples can be in the training samples. Potentially they could be here, but this is a big table, so I'm just making an assumption on that. So we have our training and test set. And the first function that you should run with Caret, if you're new, is when you look at the documentation, one of the first things there is the get model info. And this tells you which machine learning algorithms you can run. And I said, today we're doing SVM. So we're going to look at the SVM linear kernel or implementation. There are things like random forest, so RF here or Ranger. And actually what Caret does is it just wraps around existing libraries. So if you were to use the random forest library, call to Caret, it will just use the random forest library in R. If you use SVM linear, what we're doing today is just a wrapper to the E1071 library, which is what where we found the naive Bayes package, and it also has SVM implementations. So there's a lot of different machine learning algorithms you could try. I've no doubt people just write for loops to go through each one and tune each one and just read off the best classifier. Yeah, you could, explore these to your heart's content. Okay, so we talked about sampling methods. So we want to tell Caret how we want to run our machine learning experiment. And we can use this train control function to specify things like we want to do crossfold validation. We're going to use k equals 5, so 5 folds. And that we're telling Caret to save our prediction boundaries, or which class it is, and also the predicted probability. There's actually way more parameters you could set in this train control function. If you output our control object, which we save this into, you can see all the possible parameters that you could have put in. So lots of these I don't even use that much. You can specify things like the cutoff for training. So you could do this up front if you wanted to. I'm going to show you a method further down to compare your results and pick an appropriate threshold for sensitivity analysis. But the point is, there are lots of parameters you can put into this function. You can specify things like, here's another one, alpha level in significance. Usually it's set to 0.05, but you don't have to accept that. Anyway, let's have a look how you actually use our control setter to run SVM. So it's the same function, no matter what algorithm you put into caret, random forest, SVM, neural nets, doesn't matter. You use the train function, and it looks really similar to what we've been doing before. Our class column that we want to predict on is the labels column, and we're going to use all columns. So use the shorthand notation. And again, even though we're doing crossfold validation, and it does things like further subset each training set into a training set and a test set for each fold, we're still only going to use our training data at this stage. So, the crossfold validation is only used in training. We're specifying SVM linear as our method. So we're going to tell the train function to use SVM, and we're going to say that the control method, i.e. how we run the experiment, is defined by our control object we specified up here. So the output of SVM fit, if you just output it there, this is basically like the top line summary of what's in this object, which is quite useful because it tells you during the crossfold validation, when you averaged out all of these samples, you achieved an accuracy of 90%. And this kappa, this is the agreement on individual data points. So if, for example, we have k equals 5, if, for example, the same data point ended up in 3 test sets during crossfold validation, this is how much on average they agreed across individual data points. So that's useful, again, looking at stability. This is like we've got 5 expert opinions, and across the 300 different patients that came in, either 300 rows we put into SVM, 80% of the time, 79% of the time, they agreed on the diagnosis. So that's another handy thing, and it's based on something called Cohen's kappa. So here we have the tuning parameter C, which is held constant at a value of 1. We'll come back to this in a bit on how we can use different values of C using caret. But just to, I think this is good practice. So any object which you've saved as a result of a function, like, we have train, we save it into an object called SVM fit. What you should always do in R is to explore all the objects held within there. So you can use this function called ls svm fit. So if you're familiar with Linux, you can list the files in a directory using this. In R, you can list all the objects within an object. If you're of the tidyverse persuasion, you could have done something like this. SVM fit, and chain that into the ls command, and it will do the same thing. Okay, so you can see there's quite a lot of objects stored within there, and we can access these with the dollar symbol. So we've got a sub object called results, and we can access that using $results, and it tells us, what our accuracy was. And probably one of the most important ones is this pred object. So we have pred in here. So we access this with the dollar symbol, and we end up with a table. And what this is that it contains the observed predicted classes, and as well as the predicted class probabilities for every sample that was using the test set for each fold. So if we scroll down, see it goes all the way down to fold 5. So, this is handy, and any one given data point, so we can tell from the row index, this might have been used in fold 4 as well as in the test set in fold 4 and fold 5. And so, what caret does is it averages out the class probabilities for you to make the final decision. And once we've trained our model, we didn't do anything fancy. We just did crossfold validation. We didn't do any hyperparameter tuning. What we can do, we can use that model, SVM fit, and we can predict based on the test set. And we're going to create a confusion matrix. So the first parameter is the predictions on the test set. The second parameter is the ground truth of the test set. We could have got this, by the way. This is equivalent to this column here, obs. So we could have put that column in as well. We could have done something like this. SVM fit $pred $obs. That is the same as that object there. So caret is storing a lot of information for you on the fly. And what you'll see, this confusion matrix function from the caret package is really nice, because previously we'd only been creating a simple contingency table, but now the confusion matrix function in caret gives you a lot of extra information. So things like the sensitivity, the specificity, and so on. And yeah, our p-value as well. So is our result significant? I would argue, you know, usually we're setting alpha to 0.05. So if we were to take a random sample or lots of random samples, we would see this same trend or the same results of our confusion matrix just over 10% of the time or 12% of the time. Okay, so just this last line here, I think is a bit problematic, because the caret has assumed that the positive class is the benign class, i.e. when we say things like the true positives are in the top left of our confusion matrix, we normally think of a true positive in the case where we've predicted that it's disease causing or pathogenic, and it is actually pathogenic. In this case, caret has assumed that the positive class is benign. And I think we should reverse this. I think we should always ensure that the true positive cases are when you say positive is like the disease class, or that you would have had lung cancer or something like that. And the reason why caret does this is if we look at our categorical variable labels, which holds values for pathogenic and benign, they're arranged in alphabetical order, and caret just looks at the first one and assumes that that is the positive class. So I think that's something that really important that you need to take into account when you run machine learning with caret. It will assume the positive class, and it will get it from the levels in your factor variable. What we can do to reverse this, to reverse the order, is use the forcats library, and it's called for forcats for categorical variables, and it's a library that can do a lot of manipulation on categorical variables. There's one function here called factor relevel, and we're just going to put in our training labels and manually specify the order so that we arrive at this. And again, we need to do the same for the test set as well. And actually, you'd probably want to do this before you even split into test and train, so you write less code. Now that we've done that, we just rerun SVM. This is the same setup as before, and this is our confusion matrix. So here we can just see that the positive class is now pathogenic. This leads us on to hyperparameter tuning. So we've covered sampling methods and how you run a simple machine learning algorithm in caret. So let's look at how we can alter this value of C, nudge it along, and see what the corresponding accuracy is when you do that. So to find out what parameters you can iterate on, there's a nice function in caret called model lookup. You just put in the model that you're interested in, and out pops out the parameter that we can optimize. And so what we can do is we'll take this parameter, and we're just going to have an object which is going to be a sequence of values that we would like to use for C during SVM. There's a few ways to do this. Caret has its own built-in function called expand.grid, which will say, I'm going to expand on C, where the value of C is equal to a sequence starting at 0.25 and adding 1 each time, up to 5. So these are different values of C. There are different ways you can do this kind of thing in R. So there's a nice function called sec or sequence, which just comes from base R. And we can say, we go from the value of 0 to 5, and we nudge it by 0.1 each time. So there's various ways you can do this. I'm just demonstrating the original caret function to do this. But yeah, you get the picture. We're setting up a grid. In this case, this is a one-dimensional grid. If you were tuning on 2 parameters at the same time, then you would have a 2D grid. Okay, so just to output our SVM grid object to remind us what the individual values are, this is what we're going to use for C. And to include these in our new setup, we just add this new parameter to train called tune grid, and it takes in our new object SVM grid. This means that it's going to take 5 times as long as before because it's going to run SVM with crossfold validation, and it'll do that each time for each different value of C. So yeah, these are different values of C. And this is you can see it's reflected in the output, because once it's run, we can just get our top line summary of SVM fit tuned, which is our new model. And you can see that we've got 5 different outputs for accuracy, and handily, the caret package will just tell us that the best value for C was this in terms of accuracy. Again, we can plot this if you wanted to, just to see it. I think it looks a bit dramatic. The scale is so small on the y-axis, but you can see how it increases and decreases. Okay, so that's how you can manually set up a grid. Another way you can do this is to just take random values. So before we had, if you looked inside, I will show this now, our control method, you know, we set up crossfold validation and so on. There was a parameter called search, and by default is set up to use grid search. I manually specify a grid. We can actually set that parameter to equal random instead. So let's just scroll back down. We can say search method equals random, and we can swap out our tune grid parameter in the train function to tune length. This just means we're going to select 20 random values for C. So again, this runs 20 times now, so even longer. And once you run it, again, you can see 20 different results. And the train function, or the summary of fit tuned, it nicely just says the best value to use was this. So that's hyperparameter tuning. The third thing we need to talk about then is ROC analysis. So this is where you have your class probabilities, and what we would usually be saying is if the probability is above 0.5, then we will call that the pathogenic class. If it's below 0.5 or equal to, then we'll call it the benign class. ROC analysis allows you to visualize what might be a better threshold to use, depending on if you're interested in maximizing sensitivity or specificity. You can go either way. And so there are two stages where you would use ROC analysis. The first is where you want to find this appropriate threshold, and you do that during training, as you would with the crossfold validation and the hyperparameter tuning. At the end of the day, it's just another parameter to tune, if you like. And the second stage you would use ROC analysis is like when you report the final accuracy of your model on the independent test set, where you get your confusion matrix, you also do an ROC analysis on the independent test set as well. So it's just like reporting accuracy. Okay, so just remind us where we got to before. We got to the stage where we had a trained model. This is the untuned model. And we could predict on the test set and create a confusion matrix. So this is the accuracy on our test set. So this is good. You should always report this. And what we can see, I don't know if you've noticed, but during training, we had slightly high values for sensitivity and specificity. Because we're using the test set now, you would expect this to come down a little bit. You know, this is the overfitting problem coming in. And what we would like to do then is create a Roc curve. And to do this, we need two things. A bit like the confusion matrix, we need the observed or the ground truth labels. And we also need the predicted class probabilities. So the input to an ROC analysis is exactly the same as the input to a confusion matrix. We just use a different function. Instead of using confusion matrix, we use this function called ROC curve. And this comes from the yardstick package. So all I've done is I have, and remember, we're doing this on the training data now to get our threshold we want. So instead of going back to the predictions on our test set, we need to go back to what was outputted to us in our training set. So again, this comes from our SVM fit object. Remember, these predictions, they are based off the test set during crossfold validation, and they are averaged out at the end. So we take our observations, this is the ground truth, and these are the averaged out class probabilities per data point during training. So we put these into our ROC curve because we want to find a threshold based on our training data. I've just saved these two. Oh no, I haven't saved these two. Actually, they come from SVM fit. What I'm going to do is do a dplyr a chain, a piping method. So I'm going to take this object SVM fit $pred. I'm going to pipe this into the Roc curve, and I'm using the column observed and the column the predicted probability of being pathogenic. These two lines, don't worry too much about this. You probably would have noticed that in Kaggle tables or data frames, the rows get truncated, and I'll show you this now. Yeah, here we go. So it truncates our output, and I want us to see the whole table. So the way I can do this is to convert a data frame that comes out of the end of the Roc curve function into a tibble, and a tibble is just the tidyverses version of a data frame, and it offers you a bit more functionality because I can say print the number of rows of this tibble explicitly, and I'm setting this to the length of the samples in our training set. The output, as you can see, is interesting. You can see for various thresholds, we get resulting specificity or sensitivity. So this allows us to choose a threshold which we would want to produce. If we were more interested in sensitivity, for example, we would choose a low threshold. So anything below this threshold is classed as benign, and anything above the threshold is classed as pathogenic. And this would result in a higher sensitivity. So I'm going to show you how to take threshold values, and we'll take somewhere around 0.01 because we want to maximize our sensitivity. And we'll take this threshold and recompute our confusion matrix. So what we do, this is a bit to unpack this cell, but let's just have a look. We need remember, two parameters into our confusion matrix. We need the class probabilities from the test set, and we need the class labels from our test set as well, so the ground truth. What we can say is if we take our class probabilities, and again, we get pathogenic and benign, I'm going to say that if the threshold, if the probability is below a certain value, and I'm going to use the threshold for this, then we're going to reclassify the result as pathogenic. And I do this here, just adding this on. So I'm going to show you what this looks like. Okay, so what this is, oh, sorry, hang on, 0.01. Okay, so what this is saying is that in this particular position, the class probability was lower than 0.01. So we're going to say that, is it pathogenic? No, it's not. It's false, i.e. it's benign. In other cases, we're going to say, okay, it's true. So this was greater than 0.01. So that's how you would reclassify samples as pathogenic or benign based on a threshold. And again, the second parameter that we need to put in are the class labels. And you're used to seeing it looking like something like this, pathogenic, benign, and so on. What we would like to do, or what we need to do to create a contingency table, is to get these to equal true or false. So we just simply say, is the label equal to the string pathogenic? And it will reclassify these as true or false. So now we have everything we need to rebuild our confusion matrix. Just one thing, the outputs of these two commands do not result in factor variables. They're just string or character vectors. So we can manually reset these as factors if we wanted to, which will take a few lines of code. If you just wrap it up in the table function, it would put it into factors for you anyway. So this is why I use the table function again. And yeah, so let's have a look at our confusion matrix. This is the result of using our new threshold. And as you can see, we've boosted our sensitivity a small amount, but we have 100% false positives in this case. So we've traded off sensitivity for specificity. So that's how you would use an ROC analysis to pick an appropriate threshold during training and apply that to your test calculations at the end. So yeah, this cell just explains a bit more about what was going on in the previous cell. Okay, so now we would like to report the ROC analysis on our test set as well, just like we would when we compute confusion matrix on our independent test set. So we're just going to save a few objects. So we use our predict function to get the class probabilities and the predicted class, and we're going to bind that with our ground truth labels, as we see here. Yeah, so we can save these objects. So with the ground truth, our predicted classes, and our predicted probabilities into a data frame, like so. And this is really handy thing to do anyway, because you have a nice, neat table we can do some stats on. The stats we're doing right now is ROC analysis. I just rename some of the columns to something better, because currently they inherit the names from cbind. Actually, you can specify the names within the cbind command if you want to, but anyway. So we have a nice table, and we just look at take the head of that table to look at the columns, what they look like. And again, all we're going to do is use the same ROC curve where we put in the ground truth and the predicted probability. So in this case, I put in benign just to show you that you can do that. And instead of just leaving it there, if you were to do this, you would end up with your data frame, which looked like this. You see, we're going to put it into the plot command instead. Autoplot. Okay, and this is how you see when we say that ROC analysis allows you to visualize all the thresholds in one graph. This is how it's doing it. It's taking the background data of the ROC function, which looks like this, and it can plot the sensitivity against the specificity across all thresholds. So it's a really nice visualization when you plot an ROC curve. And you can clearly see that at some points, you can pick a point, if you like, along this line, which denotes a different threshold, and you can read off the corresponding sensitivity and specificity. So you could have produced this curve in the training data as well. We just demonstrate how you could pick a threshold. So there was this one other thing, that area under the curve. So remember, the area under the curve is kind of another measure of accuracy, if you like. It tells you what the total accuracy you could have achieved using all thresholds. So no matter what threshold you use, if you just went through them all, this was our absolute limit of accuracy across all thresholds. And it's a very simple function, just ROC underscore AUC, the exact same parameters you input to the ROC curve function, and there you go. So no matter what threshold you chose, the absolute upper limit of your predictive power of your model is you would still have a remaining 1.2% error, no matter what threshold you chose. So this can kind of be used instead of accuracy as well. And again, you can input two. I think it's always good to put these models side by side. So if you've got two different models, our original SVM fit and our SVM tuned, to put them side by side, have the two confusion matrices there so you can see the output, but also put them on the same ROC graph. That's a pretty good thing to do. So again, this code is just repurposed on the cell above, just for our tune data, and we carry it all the way through to put it into our ROC curve. And so how we do this is we are going to take our two tables. Remember, we had a table like this for our normal SVM model. We also have a table like this for our SVM tuned model. So we're just going to combine these two, row bind them. So the table becomes twice as long, if you like. And we're going to keep track of which model produced which row of data by using column bind. So we say that our original predictions, this is the untuned model, we're going to just add a column which has a fixed value of SVM fit throughout the whole thing. And we'll do the same for our tuned data as well. And then what we do is we use row bind or R bind in R to bind these two new tables together. So you end up with something like this. So here are all the rows for our SVM fit, our original, and here's the rows for our tune data. And this is simple because now we just have to add in one line to our Roc Curve cell, and this is group by, and the column is model. And when you do that, autoplot immediately knows that we've got two separate groups, and it does the legend for you and all things like that. So, and you can see here that depending on which model you chose, you can, if I need 95% sensitivity, then I'm going to go with whatever the model is. So probably this red model here, because if you read across, or actually the best thing to do is to reproduce the threshold table as in here for both curves, and you could just read off, if I want 95% sensitivity, then I will choose this model because it achieves it better than the other. So that's how you would use Caret. I was just messing about with something here. I will delete this cell. What you would want to do now is you've got two curves, SVM fit and SVM tuned. You might want to try random forest as well and put another Roc Curve on here and just compare which is the best. But that is how you can do. Caret is a really useful package in R. It helps you automate a lot of this tuning. You can just use the same code to wrap around a different model, and you can compare models side by side. So that is typically what you're doing with a machine learning project. You have some data. You're going to test it out on multiple models, multiple different values for hyperparameters, and just pick the best one. And the ROC analysis can really help you out in tuning to the particular problem you have. Perhaps you want to pick up all the people that do develop disease and so on. So I hope you enjoyed this notebook. Caret, these kinds of workflows, they are a staple of machine learning in R. So yeah, you really want to invest a lot of time in learning all about the Caret package. So next we will be looking at unsupervised analysis tomorrow, before we go on to neural networks.